All right, how's it going, everybody? We are here at the beginning of week 5. We're going to start talking about chapter 4 this week. We just covered chapter 3 last week here, so we're going to keep moving on here. Before we get started, I just want to point out that we are looking for us to take our first test here soon. My original plan was for us to be taking our first test this week, but I think our content will just line up a little bit better if we do that next week. So this week now I'll send out an announcement about stuff that we're going to take a test over next week, the format that we're going to do that for. So be on the lookout for that. I'll throw up a page in Canvas on this week's module, kind of informing you of what to expect for a test situation next week here. So today we are looking to talk about probability distribution functions, and we're going to start by looking at how the distribution of probabilities associated with discrete random variables. So this is like the longest, wordiest section title in the book right here. Probably the distribution function for a discrete random variable, most syllables in a section title in the book. What we want to do is make sure we understand actually what this is even referring to here, and then look at some examples of what do we use these probability distribution functions for. So what does it mean to be a probability distribution function? So let's understand what this thing is that we're even looking at here. What is this object of interest? Um, and so, okay, it's working. So what does it mean to be a probability distribution function? A probability distribution function is any information that fully describes all the probability associated with all possible outcomes of an experiment. So what we're trying to do here is say a probability distribution function tells us what are all of the possible outcomes of an experiment and what is the probability associated with every single one of those possible outcomes. So some of the important things to realize here is that this thing needs to discuss everything that can happen. If we are a probability distribution function, then it matters that we represent all 100% of all possible outcomes. We want to list all of the outcomes, and we want to say exactly what the probability of experiencing that outcome is going to be. You should notice again that today we're talking about discrete random variables. So we are talking today just about the variables for which there are, in a sense, only a finite number of values that they can take on, right? This might be like out of a 5-day work week, I either work 0 days, 1 day, 2 days, 3 days, 4 days, or 5 days. There's 6 possible answers that we could come up with right there as far as the number of days that I work in a week. This is a discrete variable. My outcomes will always be one of those 6 numbers, and I could come up with a probability that I will work any of those numbers of days per week. Right? So this probability distribution function, again, it's all possible outcomes and their associated probabilities here. Some of the things that we see are we've been seeing some tables in the textbook for these. What I want to distinguish between here in this statement right here, how do probability distributions differ between discrete and random variables? In a discrete setting, there's only a finite number of possible outcomes, right? Like I just listed. What we could do here is say, for our example, we could say X is the number of days worked in a regular 5-day work week. Maybe I've been sick, maybe I've been lazy, something like that. Then what we could do is we could describe this variable as a discrete random variable. It's discrete because you're always going to tell me a whole number of days. So our probability distribution function might be best given in a table here since this is a discrete variable. And so maybe I can list here the possible values that X is going to take on. And notice that X is going to take on values 0, 1, 2, 3, 4, 5, and 6. And so we're not only listing what are all of the possible outcomes associated with this experiment here, a trial. Maybe we're polling each person at a company to see how many days per week they work that week. Everybody's answer is going to be, oops, sorry. I'm thinking to myself, there's 6 possible outcomes. I'm not working 6 days in a week. I'm going to work 0 through 5 days in a week. I added on that whole extra column for nothing over there. The other thing that we're interested in is seeing what is the probability of experiencing that outcome? What's the probability of X? Well, I'm going to go ahead and say there's only a very tiny chance that I'm not going to work at all in a week. There's only a very tiny chance that I only work one day. There's only a very tiny chance that I work 2 days. Every once in a while I'll only work 3 days in a week. And maybe it's relatively common for me to sometimes only work 4 days in a week. Maybe I'll give that a 0.25. And my question for you guys then might be, what then, therefore, is the probability that I'm going to work 5 days in a week? And the answer here is that since this is a probability distribution function, I need to describe all possible outcomes here. I am kind of assuming in this case I would never work 6 days in a week. So what I'm kind of noticing here is 0.01 plus 0.02 plus 0.03 plus 0.1 plus 0.25. Well, if I add up all these guys here, I'm getting 0.06, 0.16. Add it to this guy, I'm getting 0.41. So it looks like there's a 41% chance that I will work 0 through 4 days in a week. So if I want to fully describe the 100% of chances that I've got to work some number of days in a week, I can just find the remaining parts right here. And it looks like this will be 0.59. So it must be the case that this is a 0.59 because it's always going to be the case for a probability distribution function that all of the probabilities need to add to 1 or 100% because we want to make sure that we have accounted for all possible outcomes right here. So again, this is a good way to describe a probability distribution only for really a discrete variable. What you should realize is that if we're talking about a person's height or a person's body temperature, there might be hundreds of different actual measurements that we're taking right there. It might not be very well described in a table. It might be better described with a graph or with an equation. So giving probability distribution functions in the table is really something that only happens in a discrete setting right here, because in a continuous setting, oops, that's the wrong word. In a continuous setting, it's way, way harder for us to actually make a list of all possibilities. In a continuous setting, we're sort of saying the variable can take on literally any number in an interval rather than a whole numbers only or something like that that we see in the discrete case right here. So again, when we see these tables here, we've got the events are each of the values that our variable of interest can take on. Our variable of interest is numbers of days worked. The sample space for X, we would say is 0, 1, 2, 3, 4, 5. It's the 6 possible outcomes that we could ever see. Nobody's going to give us a response that's other than these 6 numbers right here. And here we're describing what is the probability of any one randomly selected person giving any one of those responses right there. So notice that what we're kind of doing here is we're swapping out actually having data, right? If I'm polling 100 people in my company, what I'm not looking at here is the raw data of their responses. What I am looking at here is the probability of seeing any one response for any one person, or equivalently, we can think of these as the proportions of people that give these responses. We could say 59% of people work 5 days in a week at the company, or we could say if we pulled one random person from the company, there is a 59% chance that that one person works 5 days in a week. There's really 2 different ways that we could interpret those. One is a collective statement, one is an individual statement there. So on the other hand here, how do we compare this to our other situation here? Well, when we look next week, next chapter is going to be our continuous random variables. And I just want to suggest that our distribution functions aren't going to be given to us in the same way right here. So some things that are typical then for us to see for our continuous variables is we might see like a function. I'm going to go ahead and try and remember something now that I'm going to get wrong. So we are going to look for, like most of the semester, our most important probability distribution is going to be the normal distribution. You should notice in this case what I've done right here is I've drawn a bar graph. And what we're really trying to picture for ourselves here, and we can kind of do the similar thing in this previous example, is we should see that we've got these real tiny probabilities that are associated with our first things. We're getting a little bit more probability at the 0.1. We've got our 0.25, and we've got like our 0.59 might be all big and tall like this, right? In this case, there were only 6 outcomes, so I've got 6 different columns that are visually representing each of my probabilities. But you should see that if we broke this down into more and more and more columns, maybe instead ask people, how many hours per week do you work instead of how many days per week? Then instead of giving a number between 0 and 5, they might report a number between 0 and 40 or 0 and 50. We'd have a lot more bars. But I would expect them to, in general, take on this shape because I'm thinking that the people are working 5 days a week are probably also working lots of hours. It's probably not that they're working 1 hour each of 5 days or something like that. So what we're trying to kind of picture in our heads is that we're getting these histograms that we're in a sense maybe thinking of the more fine breakdown turning into this probability curve out here instead of a histogram of probabilities. So very similarly here, we're going to see this, let's see, I think this is something like this. I think that this is the very, very, very tough formula to work with right here that's associated with our bell-shaped curve. I think there's maybe like a 1/2 sitting right here. I don't remember. Anyway, the point is when we're talking about things that are continuously distributed where we can like get any possible answer in an interval right here, when I ask what is the probability that somebody is of a certain height, then there are an infinite number of heights between 4 feet tall and 7 feet tall if we want to measure finely enough. We could compute the probability of any of those given heights being one of those heights using perhaps a function like this. So don't worry about this function being gross. It turns out that this function does give us the bell-shaped curve that we're going to use to interpret lots of continuous probabilities in the next chapter out there. But the point is, when we talk about a probability distribution function, it looks different depending on our setting. In a discrete case where we can just list each of the possible outcomes, it's generally a good move to just put our probability distribution information in just a table because we can list every outcome and exactly its probability of occurring. When we get into our continuous setting, we can't really just list things in a table because there's not a listable number of heights that a person could be, right? And so in this case, we need a more continuous way to describe things. And it's very often the case that a function, or often it's helpful for us to picture a curve to help us think about what these probabilities are going to end up being out there. So we'll see some different stuff in our continuous setting here rather than the tables that we're seeing now. So the tables that we're seeing now are very specifically associated only with discrete random variables when we can list all possible outcomes 0, 1, 2, 3, 4, and 5 and their associated probabilities that must add up to 1. So that's all that happened really in 4.1 is they showed you what a probability distribution function looks like. They defined it to be a list of all possible outcomes and their associated probabilities. They say that the 2 rules for our probability distribution function is that all probabilities need to be between 0 and 1. That makes sense. There's never a negative percent chance of something happening. It doesn't make sense for there to be a more than 100% chance of something happening. And all the probabilities have to add up to 1, meaning everything needs to be accounted for. It's not okay for you to say that something's a probability distribution function if you've only talked about 90% of the possible outcomes. It has to represent all 100%. And so the book shows some examples where they're like, oh, could you fill in the missing gaps right here? And just like we did, we can just fill in the missing gap with whatever takes us to 100%. So that's our definition of these probability distribution functions. What we want to do is we want to see in what way do we actually use these. And as I kind of said at the beginning, really our move here is to recognize that what we're thinking to ourselves now is we are not being given the raw data anymore. Now all we're being given is the information about how to expect the raw data to be spread out, but where we don't actually get the data. All we're getting is saying, hey, listen, you should expect 40% of your outcomes to look like this. So what we want to do is we want to decide how can we still compute things like average and standard deviation, even if we weren't given a data set, if we were just given sort of the information of the spread of the data within a given data set. So let's go ahead and look at this first example right here. And the first thing that we really want to make sure that we identify here is that we want to recognize that this expected value is just the same thing as average or the mean. These are all the same words for, or different words for the exact same thing. Expected value, average, and mean are all the exact same thing. We use expected value more often in the setting where you're not literally adding up the data points and dividing by the number of data points because, again, we haven't been given the data points here. So what we want to do as our first example right here is we want to determine the expected value or the average roll associated with rolling one six-sided die. This is sort of our most classic probability scenario here, rolling one six-sided die. So to answer this question, you should notice that we haven't been given any raw data. It's not like I'm saying I rolled a die 20 times and here are my results. I don't have that. And the other thing we don't have right now is we don't have a description of what to expect for each individual roll. But the good news is we're all smart people that have a good idea of what it's like to roll a six-sided die. So what I'm going to do is I'm going to kind of set myself up to first I'm going to describe the probability distribution function. Then I'm going to use that PDF, probability distribution function, PDF. I'm going to use my PDF to help me determine what should I expect on average when I roll a six-sided die. What is the average roll associated with a six-sided die? What I'm going to do is I'm going to define my variable. So X is going to be what number did I roll on one roll of the die? I know how this should work. I know what the probability is of each possible outcome in the roll of a die. I know that I can get a 1, 2, 3, 4, 5, or 6. And I know what the probability is that's associated with each of these. There's a 1/6 chance that I'm going to get any particular one, right? In a fair die, everything is equally likely to occur. And so if I divide up 100% of my possibilities over 6 equally likely outcomes or events, then in this case here, we're going to see that there's a 1/6 chance of each of these things occurring. So what I want to think to myself here is I want to think to myself, I know that I could roll this die millions of times if I wanted to, right? I could devote the rest of my life to rolling this six-sided die a million times, and I could add up all of the results that I get and divide by the 1 million rolls that I've done. Obviously, I don't want to have to do that. What I want to instead understand is that what I expect is that regardless of how many times I roll the die, as long as I roll it a large number of times, I should expect 1/6 of all of my rolls to be a 1. So I'm expecting one, so I'm going to call this here our expected value. And I'm going to say here that I expect that 1/6 of all my, oh yeah, this doesn't, for some reason, my pen does not write the same way as it wrote last week, and it's writing with a different pen function that doesn't now have the same setup here for me. It's very confusing. So I'm thinking here that 1/6 of my rolls should be a 1. I think that 1/6 of my rolls should be a 2. 1/6 of my rolls are going to be a 3. 1/6 of my rolls are going to be a 4. A sixth of them are going to be 5. And a sixth of them are going to be 6. Right. I kind of want to show you like why this is a sensible thing for me to do for my math here. I'll show you like an alternate way to think about this one here in a second. So if I add up all of my probability times value plus probability times value that we're adding up here, I'm going to get 1/6 for the first one plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. And the good news for us is we're adding fractions, but they all have a common denominator already. So I'm going to try and do some quick math here. 1 and 2 is 3, plus 3 is 6, plus 4 is 10. 10 plus 11 is going to give me 21. 21 over 6. I know that 18 divided by 6 is 3. So that's going to be 3 with 3/6 left over. So I'm going to be getting 3.5 for this guy. So This is always my kind of first expected value example that I always do. It's always a pretty easy one to do, but it leads us to this kind of strange conclusion right here. What I'm asking you is if I were to roll a die many, 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 many times, what would my average roll be? And the very strange thing that just happened to us is we got an answer that's not actually something we can roll with the die, right? 3.5 is something I've never rolled on a die before, but I've rolled about a million dice in my life, right? I've never rolled a 3.5 once. But you should notice that 3.5 is exactly sort of what sits at the dead center of our probability distribution since everything is uniformly distributed. Uniform distribution is a word that we'll end up using next week out there. 3.5 really is what's in the middle. Right? It's sitting right there. It's our most average thing to do. So another way that I think is good to think about this doesn't feel like we just computed an average to you, I'm assuming. Um, So here's a different way to think about this one as far as computing this average. Suppose I were to say to you, let's roll this six-sided die 60 times and tell me what your average roll is. Well, what I know to expect here, and now, again, what we very much know is that there is variability in every sample. To be perfectly honest, I don't actually expect to roll each of my six sides of the die 10 times here, but I do think that is the most likely outcome right here. An even distribution. It's what's most likely is for each thing to be rolled the same number of times as each other. So if I were to roll this die 60 times, then I would expect to get a 1 10 times. I would expect to get a 2 10 times. I would expect to get a 3 10 times, a 4 10 times, a 5 10 times, and a 6 10 times. And I've rolled a grand total of 60 times, right? This would be like my theoretical average for rolling 60 dice. I would expect to get 10 of each roll if I rolled it 60 times. That's my most likely thing because it is uniformly distributed. And what you should notice is I could actually rewrite this differently right here. Notice that every single one of these guys has a 10 in them, and that every single one of these guys is being divided by 60. Well, it seems to me that I could actually just write this as 1 times 10 over 60 plus 2 times 10 over 60 plus 3 times 10 over 60, et cetera here. And hopefully you can see what I'm getting at is that this is exactly the same thing as how we just set up our expected value computation a moment ago. This is the same thing as our 1 times 1/6 plus 2 times 1/6 on down the line right there, which is exactly the addition we did for our expected value a minute ago. So in a sense, what we're really doing here is we are computing average in a traditional way. Right here, I added up 60 values, and then I divided by 60 because I had added up 60 values to compute an average. And we were getting exactly the same thing as we got when we just multiplied an individual probability by an individual value and added up each of those guys here. So this is really just a couple different ways to approach the concept of computing an average here. And they work out to be exactly equivalent to each other. We just typically write things that look like this one over here when we actually have been given the raw data so that you can literally add up the rolls that you got divided by the rolls that you did. We typically use this type of computation or this. And again, these computations are the same thing. We just write them differently depending on what information we were given. And this information here, we weren't given a number of rolls at any point in time. There was no sample size that we were familiar with, but we did know a sort of, in a sense, a theoretical average of 1/6 of all of our rolls are a 1. 1/6 of our rolls were a 2, etc. So this led us to the conclusion of 3.5 would be your average roll. If I rolled the die 1,000 times, added all the rolls, divided by 1,000, I would expect to see my average roll value to be 3.5 or very, very close to it. The more rolls I do, the closer I expect it to get. So let's do the same thing here with a slightly more exciting situation. This situation was unexciting because every single outcome had the exact same probability of 1/6 right here. So let's mix this up a little bit and do the same thing with something that has a little bit more going on here. So very similar question. The only difference is we would now like to roll 2 dice, and then we'll get into some gambling situations. And, well, okay, insurance is also gambling. We just don't call it that. So we have 2 gambling situations coming up here. One of them is just actual gambling, and one of them is insurance. So now what I want to know is the expected value of, and let me just add some words in here real quick, the sum of rolling two six-sided dice. So I want to roll two dice and find my total, right? That's what I want to know about now. And so to do this, I'm really going to actually need to help myself out kind of quite a bit right here. In fact, it's not even clear to me what these probabilities are that's associated with this. So let me let me just kind of stop and think about this. So what are all the things that can happen when I roll two dice? By the way, I think one thing that's always valuable in a probability situation here, basically, and anytime you're academically thinking about rolling dice, it's really good to think of these dice as being separate from each other. I would encourage you to think of them as being like a green die and a red die so that you can stop and think about which one is going to be getting which outcome, right? So what I can think is that there are six possible outcomes for the first die, and the word and tells me multiplication. There are six possible outcomes associated with the second die. So what I'm seeing here is there's really 36 total possible different things that could happen when I roll two dice. And again, what I'm saying here is that a 1 on the first die and a 6 on the second die does give me a total of 7. I'm thinking of that differently than if I got a 6 on the first and a 1 on the second. Those are opposite of each other. I'm thinking of like the green die being a 1 and the red die being a 6 versus the green die being a 6 and the red die being a 1. Those are two different outcomes right there, and we want to account for both of them here. So here's the way that I'm kind of thinking about this right here. I'm kind of thinking to myself that the minimum outcome that I could possibly get here is a 2, and that's associated with rolling a 1 and a 1. The maximum possible output I could get here is a 12. That's associated with rolling a 6 and a 6. And so maybe we can go ahead and find the spread of all of the possible outcomes that we're seeing here. So here's the way that I'm going to kind of do this. I'm going to make for myself a nice big old histogram right here. Oh man, let's see if I can actually squeeze all this in here. So the roll of a 2. My first question is, how many different ways can I roll a 2? And there's only one. It's rolling a 1 with both dice. So I'm going to denote that as a 1, 1 right there. And that's the only way we can do it. My next value is a 3, and we're asking, how can I get a 3? Well, I could roll a 1 and a 2, or a 2 and a 1. How many ways could I roll a 4? Roll a 1 and a 3, a 3 and a 1, or a 2 and a 2. Oh man, I'm nervous. I think I started this in a bad spot right here. All right, let's see if I can get it in here. Um, and let's keep going. And notice what I'm doing right now is I'm sort of making a list that I really mean to be interpreted as a histogram. The height of each of these columns is exactly informing me how much probability is associated with that particular event of getting a 4 when rolling two of these dice here. So for a 5, I get a 1 and a 4, a 4 and a 1, a 2 and a 3, and a 3 and a 2. There's 4 ways to get a 5 for a 6. 1 and 5, 5 and 1, 2 and 4, 4 and 2. And there's only one way to get the 3 and the 3, because if I flip those, that's still the exact same roll right there. For the 7 right here, we can see that we're going to get the most number of combinations, 1 and 6, 6 and 1, 2 and 5, 5 and 2, 3 and 4, 4 and 3. And so notice here, maybe what I should be doing is indicating now the total number that we've observed here. So it looks like this is 1 in 36 of our responses came in the 2 column, 2 out of 36 in the 3 column, 3 out of 36 in the 4 column, 4 out of 36, 5 out of 36, and 6 out of 36. Now, notice that what we're going to experience here when we go to say, how can I find my combinations for 8? Well, notice that we can't start with a 1 anymore to make 8. 1 and 6 was the biggest we could go with still using a 1, right? So now to make 8, I can start with a 2 and a 6, and so I also get 6 and 2. I can think of a 3 and a 5, and and a 5 and a 3. I want to keep my same heights right here. And I can also do a 4 and a 4 right there. That's all my ways to get that guy. And so notice that now we're back down to a 5 out of 36 probability. And if I keep on going right here, I think I'll just do one more. Well, maybe I should just finish this up here. 9, I'll try and go as fast as I can to just fill out the rest of this. 9 gets a 3 and a 6 and a 6 and a 3, a 4 and a 5, and a 5 and a 4. 10, 4, 6, 6, 4, 5, 5, an 11, a 5 and a 6, a 6 and a 5, and a 12. Only one way for us to get a 12, a 6 and a 6. And so what I've done now is I've looked at all possible outcomes, which are the events that are in the table. These get grouped up into their events, rolling a 2 through a 12. And in red, I have described what the probability of each of those different events is going to be. That's a 4, 3 out of 36, 2 out of 36, and a 1 out of 36. So in this case, to me, it wasn't directly obvious what were my probabilities. So I determined how many outcomes were there, how many ways could I come up with each of these different, which events do each of these outcomes end up getting grouped into? And based on how many there were in each group, I can determine what is the probability of any one of those things right there. So in this case here, I want to kind of come back and summarize what we just did right here. What we just did is we kind of showed our work for determining what would be our probability distribution here. So let me just put this in a table here. Number of rows, 2 columns. And so in a table here, I could make this look like x, p of x. And again, here are x's. What roll did we get? Down here, we're saying what is the probability of seeing that outcome here? And we saw 1 in 36, 2 in 36, 3 out of 36, 4 out of 36. And notice, by the way, this is another one of those situations where we could technically absolutely reduce some of these fractions, but then we're just going to have to work to get back to common denominators again when we go to do our addition. So I don't really have any benefit in that. These are all directly comparable to me because they all have that same common denominator. So I think this is a great example of when it's probably bad to reduce or to go into decimal form. This is easily interpretable for me now since these are all as consistent fractions here. So I think now we can go ahead and compute our expected value. And by the way, I do want to give a little bit of notation for this. Earlier we used this notation for our average to be the sum of the x sub i's divided by the number of things that we had. We use this symbol to say add up each of your entries, divide by how many entries there were. When we write our expected value computation, there's similarly the sum in here, but we just write it a little bit differently. Here, what we want to add up is each of the values, each of the individual x's, so we call that an x sub I, it's the ith x value, and we're multiplying that times the probability of experiencing that x sub I. All right, so we're adding up the products of each value and its probability. So in this case here, our expected value computation should look like 2 times 1 over 36 plus 3 times 2 over 36. The value is 3. The number of ways that it could occur is 2, and that's out of 36 total ways. And so we can go on down the line here and add up all these terms. 5, there's a 4 in 36 ways. That this is a symmetric distribution. It's centered at the event of 7, and it has exact same stuff going on to the left of 7 as it does to the right of 7. That's actually really helpful for me in kind of knowing how to like kind of arrange my work over here. Well, I was thinking about aligning these probabilities, maybe not right there, but still, in any event, it's good to notice that symmetry right there. So I'm going to kind of keep on going here. We've got 8 has a 5 in 36 chance of occurring, 9, 4 in 36, 10, 3 in 36, 11, 2 in 36, is 10. Going to be a 1 in 36. So what I want to do now is actually do all this addition here. So you should notice all of these have a common denominator of 36. And so I just want to get all of my numerator parts here added up. So all these 11 terms over 36. So my first numerator, 2 times 1 is 2. 3 times 2 is 6. 4 times 3 is 12. 5 times 4 is 20. 6 times 5 is 30. 7 times 6 is 42. 8 times 5 is 40. 9 times 4 is 36. 10 times 3 is 30. 11 times 2 is 22. And 1 times 10 is going to be 10. So now I'm just going to go to my calculator and add up all these guys. 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 10. Wait a minute. What did I do a multiplication wrong right there? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Did I just do? I'm off by like a tiny bare smidge in my calculator. I'm trying to see what did I throw in here? Plus 6 plus 12 plus 20 plus 30 plus 42 plus 40, 36, 30, 22, 10. Am I being crazy here? Oh, thank you very much, Sylvia. I knew that I was off by just a tiny bare smidge right there. I was being dumb. There we go. There's my value of 10, value of 11. This should be a value of 12. Sylvia, you're awesome. Thank you very much. This is as it goes in stats right there, right? And I'm going to show you exactly why I knew that the answer I just came up with couldn't have possibly been right. And so what I am getting now, thank you so much for helping me fix that, is 252 divided by 36. And now, before I go and do that division in my calculator right there, I want to point out that we should hopefully have a very, very, very good guess as to what our answer is. A minute ago, we just asked the question, what is the expected value of rolling one six-sided die? And we got 3.5, and we noticed that 3.5 is the center of a symmetric distribution. We are now just doing two of the dice, right? Two of the same dice. Well, it seems reasonable to me that since this is again a symmetric distribution, that our mean should be sitting at the center right here. Also notice before we got 3.5. Well, what's 3.5 two times? And the answer is it's going to be 7 right here. So I like doing these two examples kind of side by side because the first example sort of shows you what the computation looks like, but is a boring first example with all those 1/6. This one's a little bit more exciting because we actually have to stop and think for a second what each of our probabilities are by making our, and this is kind of a weird thing here too. This is sort of like a probability event list histogram. There's a lot of data that is being contained in this table that I made right here, but it was summarized nicely in this table. I would call this table our probability distribution function. It lists all possible outcomes and the associated probability of that outcome. And we can directly use it to really just multiply down each of these individual columns and add up all the terms. To do this, this resulted in us getting the event of 7. And so what this says to me, if you're going to sit there and roll 2 dice and say, what's the sum of 2 dice on average, if I were to throw 2 dice a million times, what you should find is that your average roll is a 7. And by the way, this is like a fact that is like built into like every single board game that involves 2 dice has like some special rule of what happens when you get a 7. Okay, it's an exaggeration, not every game, but 7 is this super special number because it is the most likely roll when you are rolling 2 dice. Notice that 6 out of 36 actually reduces down to 1/6. So it's actually the case that 1 in 6 times that you roll 2 dice together, the total will be 7, and that's the most common result. So 7 is very typically a very special roll in most 2 dice games because it's the most common result for 2 dice right there. It is the average roll over time. So These cases still are not super exciting because this is really just what happens when you roll dice, and we've all kind of rolled dice before. So let's look at some examples that are a little bit more interesting here. I like gambling. I don't know. That's sort of like a family thing. Like I grew up playing like blackjack with my grandparents and all kinds of stuff like that. I've when I was in graduate school, a lot of my friends decided that we would roll dice a lot, and it was a thing to like always keep a couple ones on you and some dice so that we could always like gamble for small periods of time all the time. That was like our little time filler was rolling dice, kind of a lot. I don't know how that ended up being a thing, but we did it a lot. So I like things that are like this. This is a card game right here instead of a dice game. But again, these are questions where what we want to know is it worth it for you to play that game? Should you play that game? And what we always need to do is we need to make an assessment of what is our chance of winning, what is our chance of losing, what do we stand to gain if we win, and what do we stand to lose if we win. What I always like to think about when I think of expected value for gambling games is when I lived for my first 2.5 years of undergraduate, I lived in St. Louis, and I went to St. Louis University, which was very much like a city, school like in the middle of a downtown of a city. I lived 20 minutes outside of the city in a more rural area, but there was a sort of like a public transport sort of train that went in and out of the city, the Metro Link in St. Louis. And as it goes in most urban areas, there are a pretty wide variety of people that you will encounter on the Metrolink. And so I was riding home. I was like going home to like, have dinner with my family or something, taking the Metrolink back to the Illinois side of the river. And a guy who looks like he probably spends a lot of time sort of hanging out on the Metrolink was holding, and he had with him like a piece of newspaper. He had like a bottle cap, and he had like a piece of cereal. I think it was like oh, I don't know. It was like Kix or something like that, like an individual round piece of cereal. And he was playing like the guess which cap it's under game. And so he had three different caps, and he's like moving them around on a piece of paper. And he was trying to convince random people on the Metrolink to bet him like $20 that they couldn't guess where the thing is at. And so this is one of those situations where I'm like very much trying not to make eye contact with this guy so that he'll like engage with me because I have no interest in doing that. But also like I like gambling and I have a $20 bill in my pocket and I'm like, well, if this guy's bad at this game and if I can watch it, then I should probably just do this. And so I'm sitting there watching out of the corner of my eye, and he like talks some people into the train into like doing this with him and betting. And I'm watching these people lose, but like I am easily watching him like make the swaps that he's making, and I'm like, oh, it's the one on the left, and the person's guessing the one on the right and losing, and he's like, ah, it's the one on the left, and I was like, damn. Like I should be doing this. And so eventually I'm like 5 minutes away from my stop and the guy's like, hey man, you want to bet me $20 you can't do this right here? And I was like, no, I don't, but I've been right like every single time. And so my issue right here was I had a difficulty of judging what is my probability of losing here. I knew what the value was of the win and the loss, plus $20 or minus $20. And what I needed to know was that I was going to have a high enough chance of winning that it would have been worth it for me to play that game just one time. So a lot of things in life are like this, not just when we're getting hit up by people on the street to gamble for $20, but where you need to like assess a probability of something in conjunction with the value associated with the different possible outcomes to determine if something is actually in your best interest. If you go to Vegas, there are some games in Vegas that are actually pretty close to being an even fair game, like blackjack. There's also lots of games in Vegas that have terrible odds for the player and have great house odds, and they try and pretty up those games and make them have lots more flashing lights and stuff like that to draw people in. So it really matters that you can assess what is the value that is associated with each outcome and the probability of that outcome so that you can collectively determine which of these games is going to be most in my best interest. Is this a winning game? Is this a losing game for me? How many times? What should I expect to happen if I play this game 50 times? Questions like that. So to that end, we're going to look at a gambling question right now. And then as I slightly joked earlier, next we'll look at an insurance question, which is really just more of like adult professional gambling. But similar idea here. It's assessing risk and value and determining what's going to be in your best interest. So here's the gambling game. You can pay $5, and when you pay $5, that entitles you to draw one card out of a deck. If the card that you draw is not a face card, meaning an ace or a 2 through 10, then you get nothing. So you've lost $5. If the card that you pull is a jack, then I'm going to give you back $2. But notice that still means that you've lost $3 overall because you had to pay $5 to play the game. If you draw a queen, then you're going to end up $2 because I'm giving you $7 and you paid 5 to play the game. If you get a king, then you're going to end up $10 because you paid $5 to play. So that's minus 5, but you're going to get 15 from me for drawing the king. My question to you is, should you play this game? Is this a good game for you to play? Should you expect to win money in the long run or not? The other question is, maybe you're not going to play this game in the long run. Is this a smart game for you to play in the short run? And that's going to be some questions we're also going to kind of talk about here. So let's kind of work into identifying how we can work out what's going to be happening here. So what you'll see, a typical thing is that the book does exactly this, is they make an expected value table, sort of, to kind of work out all of the events that could happen, their value and their probability. So what I want to do is I want to break down all the possible events, the value of that event, and the probability associated with that event occurring. So what are my events here? Well, one thing that could happen is I could get not a face card. What I'm thinking to myself is, out of the 13 different type of cards that are in a deck, right? Notice, by the way, here, nothing has to do with suit. Everything has to do with the type of card. There are 13 cards. Ace through 10 is 10 of them. That's 1 through 10. And then Jack, Queen, King makes 13 in total. So it looks like there are 10 out of 13 cards. Right? 10 out of 13 cards are non-face cards. And what value does that bring to me? There's a 10 and 13 chance that what is going to happen to me? Well, my overall change in value for me is I paid $5, that's a $5 loss, and I gained nothing. So my overall value here is a negative 5. All right? That says I'm going to lose $5 10 out of 13 times. Another thing that could happen here is I could draw a jack. Only 1 in 13 cards in the deck are jacks, or 4 out of 52 cards. If I pull a jack, I'm actually only going to lose $3 total because I'm going to get $2 back. And by the way, I've got this up on my other thing over here so we can reference this. I know I'm going to need to scroll. So what else can happen here? My other event of interest here is we could pull a queen. There is also a 1 in 13 chance of drawing a queen out of a deck of cards. And notice in this case, we're going to get $7. And so that really actually means we're going to end up ahead $2 every time we pull a queen. We pay $5 to play. We win $7 by getting the queen. That's a net of $2 overall. Finally, we're going to pull a king here. And to get a king, that's going to give us a total net change of a positive $10 right there, right? We pay $5. We win 15 for a net gain of 10 total dollars if we pull that king. And again, there's a 1 in 13 chance that we're going to see a king. So now what I'm going to do is I'm going to make a new column, and I'm going to call this the x times p of x column, right? This is sort of my x values. This is my p of x values right here. And what I need for expected value is I need to multiply these together. Negative 5 times 10 is going to be a negative 50 over 13. Negative 3 times 13 is a negative 3 over 13. Positive 2 times 1/13 is 2 over 13. And positive 10 times 1/13 is a 10/13. What I can now do is just add up all of my x's and p of x's to get my expected value here. So if I add all these up, it looks like this is pretty devastating for us here. Right? I'm seeing negative 50, negative 3 is negative 53. A positive 2 makes it negative 51. A positive 10 makes it negative 41. Now, I kept all these in fractions because I wanted to be able to do fraction math, right? Adding fractions right here, it's always good with the common denominator. Oops, and I wrote this wrong. Negative 41 out of 13. So what this says to me right here, I'm going to go to my calculator and ask for a little help here. 41 divided by 13. Oh my gosh, I'm even doing my 31 instead of 13 on my calculator. Is 3.15. In this case here, I want a decimal because I know that money is computed in decimals right here. So my expected value says, on average, what you should expect to happen is that your average result each time you play this game is you should expect on average to lose $3.15. Just like we saw in our first example today, no, you can't play one game and have the outcome of one game being losing $3.15. What we're saying here is if you were to play this game many, 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 many times, then what you would expect your average result per game to be a loss of $3.15 on average over many, many plays. So I kind of want to really explicitly state these things here. So I'm going to say here, we computed our expected value of one play of the game to be a loss of $3.15. So last week, one of the things I brought up in the lecture slightly preemptively was this discussion of the law of large numbers. What we kind of want to keep reminding ourselves here is that these, in a sense, theoretical expectations here of, for example, drawing a king 1 in 13 draws, it might be the case that you shuffle the deck of cards and all 4 kings are on the very bottom, right? It might be that you literally draw 48 cards in a row before you draw a king. That could happen. It's pretty unlikely. Each of these is just a probability of what we would expect in the long term to see for each of our draws here. So a really important thing to understand is that this value here isn't telling us anything about what we should expect in the short term, right? If I play this game one time, it's not even possible for me to get that expected value of change right there, that loss of $3.15. The only thing that can happen to me if I play the game once is one of these 4 outcomes right here. But again, some of these outcomes, like losing $5, are much, much more likely than winning $10 right here. And so they have more weight when we go to compute the expected value. These are, in a sense, like weighted averages. We gave 10 times as much weight to this result because this result occurs 10 times more often than each of these 3 results right here. Right? So again, expected value is not something that we ever think is something that's truly a result of doing this. Like performing this experiment one time. Expected value is a statement of what we should expect on average if a large number of trials are performed. If you were to play this game hundreds of times, then we think that we could expect an average result per game that looks like this. And I thought I asked that question here. Oh, okay, here we go. I did ask that question. If you were to play this game 100 times, I'm just going to move this down a little bit right here. Then what do we expect to happen? Well, in this case right here, we expect to lose $3.15 per game over 100 games equals a loss of $315, right? All I'm doing is multiplying the number of games times the loss per game to get the overall amount of losses right here. If we were to play this game 100 times, then we would expect on average to see about a loss of $315 overall. So this is really saying to me this is probably a pretty bad game, right? I think a game that costs $5 to play, where on average you lose more than $3 out of your $5 per game, pretty overall horrible game right here. This has terrible odds. I would certainly not recommend you playing this game in Vegas or on a train with a stranger or anywhere else. Pretty bad game overall right here. And again, we can make statements about a per game expectation, even though this isn't a realistic individual outcome, and we can interpret that one game expectation across many, many games thanks to the law of large numbers saying, yeah, this should be your average result over many games. So if you do many games, you can apply our ideas about the average per game across those many, many games to estimate a long-term winnings or losses out there. So hopefully you guys kind of understand how this can very closely relate to insurance. Insurance is also one of these things where there are good things for the insurance company and there are bad things for the insurance company. You making claims, you not making claims. These things have wildly different probabilities than each other, right? The probability that you do get in a car accident is way different than the probability that you don't get in a car accident. And what they want to do is they want to think about what is going to be a long term average expectation for how much they're going to have to pay per person. And they want to make sure that their premiums are a little bit more than that overall so that they are actually making money. They really care about this number, right? So, and I think a good thing to think about what's different between gambling and insurance is that most people at a casino, the reason casinos are capable of kind of making their money is most people at a casino don't play games lots and lots of times. They play them a few times, and if they lose a bunch of money, they walk away. On the other hand, insurance companies typically sell like hundreds of thousands or millions of policies. So insurance companies really get to rely on the fact that the law of large numbers is going to take effect in all of their transactions because it's really rare for there to be insurance companies that just sell a couple policies. It's really about there being a large number of people that own the same policy, and that kind of collective action is what allows the insurance company to still make big payouts to people when they deserve it for whatever happened, and to still have it be affordable for people that end up not having to use the insurance still to make their premium. So let's look at one other really good example here of some expected value stuff in a insurance setting rather than a gambling setting. But again, insurance is really just like very responsible gambling. It's you're making a smart bet that is going to save you money in the long run to pay into insurance over the long run because we never know when we're going to need it. So an insurance company charges $50. So all you're going to, and so by the way, I'm going to make a million little fudges here. Insurance things are so much more technical than I'm going to make them out to be right now. I hope that you all understand that. But we want to like really simplify things so that we can get an essence idea of how this really works. So the way that Tony Insurance works right here is you're going to pay me $50, and that is going to entitle you to coverage for life for one payout for you getting into an accident. The policy will pay one time ever, and once it pays out, you're never covered unless you maybe pay another $50. But honestly, insurance companies will probably not sell you the same policy back for the same amount of money if you've already made a claim. The policy will pay $10,000 to you if you experience whatever this minor accident is, and $50,000 to you if you experience a major accident, whatever this major accident is. Obviously, they have ways of judging what you're going to qualify for. A really important thing that every insurance company does is they need to estimate how many of their policyholders are going to make these certain claims. They need to know if you own a motorcycle and you're age 30 and between age 30 and 35 and you're a female and you've gotten in two prior accidents but they were both in a car and you live in the state of California, what is the probability that you will get in a motorcycle accident this year? So lots of people that work for insurance companies, their job is to collect all of this publicly accessible data and use it to make estimates for the probability that any one person will make a claim of any given value with any given policy. There's a lot of math that goes into doing that. They want to do this so that they can make judgments about how much it's reasonable for them to charge for this policy so that they're not necessarily heavily overcharging their customers so that they can stay competitive in the insurance market, but that they're not undercharging their customers in the sense that they're going to lose a bunch of money if a bunch of people make claims. So, the first question that I want to ask here is if the insurance company sells only 10 of these policies, what is their expected profit or loss? And this is sort of my dumb question to get us started right here. The deal is that there are very, very few insurance companies that sell any form of policy that they're ever expecting to sell to only a very small number of people. So notice here that when there's only 10 policies getting sold, there's only kind of a finite number of outcomes that could possibly even happen here, right? So I would say here, if there are 0 claims, then they have a $500 profit, right? Because they sold 10 policies for $50 each. So they just made 500 bucks. Nobody made any claims. Nobody had any accidents or injuries. And so they just pocketed that $500 and everybody's happy, right? But notice that if there's even one claim, then they brought in $500 in revenue, but they lost either $10,000 or $50,000 for an accident. And so I'm going to say they lost $9,500 for minor claim. They lost what, $49,000, $49,500 for a major claim. And so here's the deal. I'm not even going to go ahead and compute any probabilities of this occurring. I'm not going to talk about the probability that they have 2 claims or 3 claims or 4 claims. What you should realize is it's incredibly, incredibly difficult for an insurance company to make any judgments about what they should expect if they only sell 10 policies for something. Our issue here is that 10 policies is not enough for the law of large numbers to take effect. So that we can reasonably estimate any long-term averages, right? The worst case scenario for any insurance company is that one claim is the difference between them making money and losing money. That is the absolute worst place that an insurance company could ever find themselves, is one claim making a massive difference in whether they have profits or losses. So what I would say here is it's really hard for them to make some sort of expectation of what's going on here because one person could make a huge difference for them, right? So this is a bad, bad insurance situation. So my answer to this question is it's very difficult for us to make a reasonable expectation here because 10 policies just isn't enough for our averages, for our experimental averages to be able to approach our theoretical averages. We could compute an expected value here, but it wouldn't necessarily be reflective whatsoever of what would truly happen in a 10 policy scenario, right? 10 policies just isn't enough for us to make a reasonable estimate of what we expect to see. Now, much, much, much more reasonably is if the insurance company sells 10 or 100,000 of these policies, what can we expect? And this is a little bit more like what's typical of an insurance company right here. They need to bulk sell policies to protect themselves against, all it takes is one hailstorm and they might have hundreds more policy claims than they thought. There needs to be so many policies that even a hailstorm going through a major city doesn't wildly affect their profits and losses. So this is way more typical for an insurance company, something where they're selling hundreds of thousands of policies. So let's go ahead and do what we did before and come up with this same profit loss scenario. One thing I'm going to do a little bit different here in this table is this. In this table up here, when we computed our value in this table was truly the profit associated with one game. A profit of -$5 because we had -5 plus 0 made -5. -5 plus 2 made -3. -5 plus 7 made +2, stuff like that. I'm going to break this down a little bit differently here. And instead of having this be the actual profit over time, I'm just going to have this be the actual numbers that we saw right here, like the 2, the 7, the 15. So I'm going to set up my table a little bit differently. You can decide for yourself which of the ways that you like to present this stuff in your tables here. So here's the way that I'm going to write this a little differently. I'm still going to make my event column, my value column, and my probability column. And I'm going to add them up over here. I'm going to make my product column and add them up. My events here, I'm going to make one event a little bit different. The event that I didn't use in the gambling situation is one of my events wasn't pay for the game, right? That was automatically included in all of the other events that I had paid for the game. In this case, just to do something different, just to show you a different way that we can sometimes write these things, I'm going to write this one just a little bit different, right? So we're going to pay for the game. Or sorry, we're going to pay for a policy in this case. Now, if I pay for the policy, the value associated with the insurance company, and again, we're looking at this from the insurance company's perspective. If one person pays for the policy, then they are gaining $50. And if they pay for the policy, what's the probability that they get $50? Well, there's a 100% chance. So I'm just going to say the probability that they get $50 if I pay for the policy is a 100% chance. Everybody involved in this has to have paid for the policy. Now, one of the things that could happen here is there could be a minor claim. If there's a minor claim, this is going to be a net loss, or excuse me, that will result in a loss of $10,000 to the insurance company. But the probability of it is really, really, really small, right? Looking over here, a 0.25%. If I write this as a decimal, that is a 0.0025, right? I've moved the decimal two places to the side. So 0.25% as a decimal is 0.0025. If there is a major claim, then the company is going to lose $50,000. But it's really rare that they're going to have that experience, right? 0.01%, I'm going to shuffle the decimal two places to the left, and I'm going to see this as a 0.0001. That's how we write 0.01% as a decimal. To convert a decimal or a percentage to a decimal, you always move that decimal place two slots to the left right there. So what I want to do now is I want to see what are all of my, and again, my values are my x's, my probabilities are my p of x's, and so I'm going to make my x times p of x column. In this case, I'm going to get 50 times 1 is 50. Negative 10,000 times 0.0025, this says get an additional 4 zeros. The 4 decimal places says lose 4 zeros. So this is, and again, you can just double check this guy in your calculator here. 10,000 times 0.0025 is just giving me 25. Right, so this is a loss of 25. And similarly, right here, negative 50,000 times 0.0001 is giving me negative 5. So again, if I go ahead and add up my x times p of x column, what this is saying to me, I've got a negative 30 and a positive 50 is an expected value of, it looks like a $20 profit for the insurance company per person. So it looks like what I could say here is that on average, again, I am not making a claim about one individual. On average, across hundreds of thousands of individuals, the average profit we should expect this company to experience from each policy sale is $20. You should notice it's not possible for the insurance company to exactly profit $20 from one sale because they're never going to make a $50 sale of a policy and then pay out $30 to me for a claim, resulting in them profiting $20. It can never happen for just one person. But on average, collectively here, since a very small minority of people are going to make very big claims that result in losses, but a vast majority of people, the other 99.65%, are never going to make a claim on this policy, in which case they just get to pocket the $50 that the people have put into that right there. So it looks like here that the company is expecting to receive on average, $20 of profit per each individual policy that they sold. And so 100 policies. So now I can answer my actual question right here. I've got question A is if the insurance companies sell, oh wait, we answered A. If they only sell 10 policies, we really can't make a judgment. That's not enough for the law of large numbers to take effect. If they sold 100,000 of these, what is their expected profit or loss? And so what I can say here is 100,000 policies, and I'm going to do a little unit math here. I just didn't write it this way last time. 100,000 policies times $20 profit per policy is going to be, so we stick on a 0, so that becomes 1 million, and we multiply by 2, so that's 2 million. So what the insurance company can expect is a $2 million profit if they sell 100,000 of these policies here. And they're going to make that profit, in a sense, $20 from each customer because the average customer will receive $30 in payout. That's because a very small minority will get massive payouts and a very massive majority will get no payout for an average payout of $30 to each person. So the last question that I want to ask here is, if this insurance company decided to suddenly just decide that they're just a bunch of awesome people and that they don't necessarily care to make profits anymore, what should they charge people so that they're just going to break even on this whole dang thing? Well, it looks like what we're seeing here is they are expecting on average to pay out an average of $30 per person And again, that's a ridiculous statement, sort of, because nobody is getting anywhere close to a $30 payout. You're either getting a massive payout or no payout. But the average is going to be 30 because so few people are getting the huge thing and most people are getting nothing, right? So it looks like since they're expecting to pay out $30, I can just say here, the expected payout to each policyholder on average is $30 per person. Therefore, if they charge $30 for the policy, they should expect to break even in the long run. Now, obviously, most insurance companies aren't nonprofits. Obviously, it's dicey for a company to do this because, like I said, all it takes is like one hailstorm to come through, and you're a home rent insurance company that costs you a whole lot of money, right? So you want to always build in the wiggle room to, in a sense, overcharge to make sure that you don't get shorted. But it's even the case that like there are sometimes like this happened to me where like Geico has just said like, oh, listen, we had like a drastically fewer number of claims than was anticipated this year, which just happened. And so therefore they sort of like return a little bit of money, or it's like you get like $40 off on your next month's premium or something like that. And they do that across all policyholders because in a sense they sort of like overcharged you. So some insurance companies even have this sort of like a part of their contract for the insurance policy that you buy will say that they'll say things like, if our profits this year are bigger than X amount or bigger than X percent relative to our policy percentages, then we will actually return money to the policyholders because they will set for themselves sort of like a maximum number of dollars per policy that they can profit on average or something. And that's just a good way to be like good to your customers so that it's not just like, oh, haha, you guys all bought fire insurance and nobody's home burned down this year. Cool for us. That just builds a lot of mistrust of the insurance companies right there. And so a lot of insurance companies, if they have that massive benefit to them, even more so, and certainly they're going to distribute a bunch of money to shareholders, but it is pretty typically the case that lots of insurance companies will, in a sense, sort of like return a little bit of money to you if collectively, on average, all policyholders had fewer claims than they expected. Um, so this is like a super tiny snapshot of how insurance companies work. You should just notice that the things that are always going to be associated with gambling games is probabilities that are reasonably likely. It's not uncommon at all for you to meet a person who did actually pull a king. It is pretty uncommon for you to meet a person that filed a insurance claim that got them a $15,000 payout in the last year, right? That's a really rare event collectively. Like I know like one person who's made like an insurance claim this big in their life, right? So a lot of insurance stuff deals with super tiny, tiny, tiny policies that are going on out here. Um, or tiny, tiny probabilities, whereas lots of maybe more gambling scenarios deals with lots of more like middle of the road probabilities that are less extreme than this one right here. And so again, insurance things are really hard to make judgments on because it's really tough for us to eyeball the comparative value of paying $50 for a policy because we're thinking like, gosh, there's like almost no chance I'm going to get in that major car accident. But if you did, you don't have $50,000 to pay for all your expenses, and that's why it generally makes sense and you should pay for insurance. Um, I go back and forth in my life between feeling like some insurance things are a scam because some insurance policies are, but for a lot of things, I mean, like health insurance, you need health insurance. In America, this is the only country on earth where you can go into debt for your life for breaking your leg. We've just decided for some reason to build a system that's like that. You are welcome to go ahead and vote for politicians that want to not make our system be that way. But as it currently stands, it is a bad statistical move for you to ever not have health insurance, even being the healthiest you'll ever be in your whole life and never leaving your house during a pandemic and not being accident prone. It is still the expected benefit to you is still great enough that every person should have health insurance and should work to pay for health insurance. It is a good purchase on everybody's part, unfortunately. And again, maybe we can all work to build a collective government system to where people don't need to worry about being in medical debt for their entire lives, or not be able to afford health insurance because it's so expensive. But that's more of a long-term, big systemic problem. Everybody should have health insurance, and it can be, I can prove to you that you need health insurance by basically building a table that looks like this right here and showing you that you could not cover the costs associated with serious injury to yourself if you didn't have the health insurance. And so it is in general a thing that people should have here. So this is where I want to wrap it up today. That actually worked out kind of perfect right there for where we ended. Tomorrow, what we're still going to talk about out of section 4.2 is we still need to talk about standard deviation. Fortunately, the standard deviation is, in my mind, it's less exciting than doing the expected value. We're certainly going to do way fewer examples for standard deviation than we just did for expected value. And we're going to see that how we do the computation is going to be like a perfect union of how we computed standard deviation last week with how we computed expected value today. That's all we're going to do to wrap up 4.2. Section 4.3, the binomial distribution, is our first sort of formally named distribution. We said what a probability distribution is today in general, but there's a bunch of special ones that come up like over and over and over and over again. So the first special one that we're going to see that gets a special name is the binomial distribution. It's going to tell us about probabilities for everything in which there are two possible outcomes. So judging male or female, judging does the person in the population have cancer or not, right? All these yes, no, these binary results are going to be associated with the binomial distribution. The really important thing to know about the stuff associated with the binomial distribution is even if you've been doing a good job of using like a pocket calculator to do some of the calculations up until right now, that sort of ends with our introduction of the binomial distribution here. It is going to be the case that you either need to have a TI calculator. I've got a TI 84 plus right here, or a TI 83 or a TI 84 silver, or any of those TI 80 somethings are good. What's going to be easier for me to show to you and what costs all of us $0 is to use Excel. So I'm going to show my demonstrations in Excel tomorrow. It's going to be equally easy for you to use your TI calculator if you've got one, but it's very difficult for me to show that on screen. I'm going to look to see if I can get a TI that I can like bring up on my display right here, but I'm not 100% positive I'll be able to do that by tomorrow. So I'm gonna plan on doing this in Excel tomorrow. So remember, if you do have a computer but don't have Excel, then you can get Excel. You can download it for free, and you can get that information at the CR website. If you want to use something other than a TI calculator or Excel, then you are responsible for identifying that. I know that some people are using like Google Sheets because you can use that even without downloading all the Microsoft Word stuff like that. I am quite certain that Google Sheets can probably do this. I haven't done it, but I would hope that you are able of Googling for binomial distribution calculator Google Sheets, and I'm sure that it will pop up a page that will say, here's how to make these computations. And I am further sure, without ever seeing what's there, that the way that you will do it in any other thing is going to look a lot like, it's going to need the same information, and so it's going to take it in the same way. So all of these things are probably going to have very, very common similarities, but we're certainly at a point in the class where we're at a point where it's like you don't have a way to do this computation by hand. So everybody needs to have a calculator that will do binomial distribution calculations for us. So kind of a bigger part of tomorrow will be making sure that we can use Excel, or you making sure that you can use your calculator to perform the computations that we need for the binomial distribution here, and look at to what applications are those relevant here. So a little bit more technology in tomorrow's video. Expect that. If you don't have Excel, download it tonight if you can. If you have your calculator, your TI calculator, and you haven't busted it out once this semester, then go look maybe at, I think I threw in the weekly guide. It's page like 243 or something like that. I'm kind of guessing a page number I remember right now. But in the book, they give you a little blurb on like how to use your TI calculator for the binomial distribution computation. So maybe just look in the book and see if you can find those numbers and stuff like that before you watch the next video here. So we'll look at that binomial distribution stuff next video. That's all I got for you today. Sylvia, thank you for your help in my one dumb that I made there in example number 2. And I will see you guys for our calculations of standard deviation and discussion of the binomial distribution and our technology used to make our computations associated with that in tomorrow's video. And we'll be taking our first test next week, and you can expect to see information pop up in this week's Canvas module about that. Probably either today or on Wednesday, I'll kind of actually get that information to you guys about what to expect for that test next week. I'll see you guys next video. Have a good one.